Welcome back to another lecture video. This is gonna be our second to last lecture for this chapter and second to last lecture of this topic that we call linear algebra. So we're almost done with this, and in this video in particular, we are not going to learn anything new. In matter of fact, we are going to get a bunch of concepts that we learned in the past and then put them all together and see what we can do with them. So let's get started. So the first thing that we're going to discuss about is symmetric matrices. And if you remember back in elementary school mathematics, you learned that a square matrix is symmetrical if its transpose is equal to A. Now, one way you can check that if a matrix is symmetrical is if it is symmetric along the main diagonal of the matrix. And what's cool about these symmetric matrices is that all symmetrical matrices are diagonalizable. And that is not necessarily the case for non-symmetrical matrices. If you remember in the last lecture about diagonalization, we did a couple of examples, and I'm pretty sure most of them weren't symmetric, but we were able to diagonalize them. And those I picked those specific examples because they can be diagonalizable. There are some cases where it is not necessarily the case. Some of them might even give you non-real numbers as their eigenvalues, and it's really easy to show them. So this is why we're discussing about symmetric matrices, because you can do so much with them despite how simple they look. And so along with the symmetric matrices, we are going to discuss about something called the real spectrum theorem. And so what the real spectrum theorem is telling us is that if we have a n by n matrix that is, I forgot to mention, if we have an n by n matrix that's symmetrical, then the following properties are true. The first one being is that A is diagonalizable, which we discussed like the last slide. The second thing is that all the eigenvalues of A are real. And then another property about this is that if lambda is an eigenvalue of A with a multiplicity of K, then lambda has K linearly independent eigenvectors, or in other words, the eigenspace of lambda has a dimension of K. So if we have a square symmetrical matrix A and we have an eigenvalue that has a multiplicity of 2, then that means its eigenspace for that eigenvalue has a dimension of 2. That means it will contain 2 eigenvectors. And that's pretty cool. It just pretty much tells us that it just pretty much enforces the fact that A is diagonalizable, because you will always find a n number of eigenvectors that are linearly independent to each other. So now that we're pretty much done with symmetric matrices, let's move on to orthogonal matrices. If you recall last lecture, to diagonalize a matrix, you need to find an invertible matrix that we called S. In some books or some professors might replace the S with a P. Personally, I like to call it S, mostly because you can just say SAS, and that's much more easier to remember. So if we have an invertible matrix S such that its inverse times the matrix A times S is diagonalizable, then you can find a diagonal matrix. Now, what's so special about the invertible matrix for a symmetrical matrix is the fact that if we take the inverse of S, we will see that S inverse is equal to its transpose. And what this is pretty much telling us is that S is orthogonal. And so because S is orthogonal, then that means the column vectors of that matrix form an orthonormal set. And this makes sense because we know that S inverse times S is equal to the identity matrix, but we also know that the S inverse is equal to its transpose. And so there's going to be a short video on the proof of this in case you're a little bit confused. So look forward to that one. And so now that we have orthogonal matrices, symmetrical matrices, what's with the whole orthogonal diagonalization. So if we have a matrix A and is orthogonally diagonalizable and has real eigenvalues, if and only if A is symmetric. And so how does this whole process with diagonalizing this matrix that we call A orthogonal? So as always, we're going to start off with our givens. We're going to let A be an n by n symmetric matrix. It's important that it is symmetric. And so the first step is, as usual, you find the eigenvalues and determine the multiplicity of each eigenvalue. And now we're going to start dealing with the eigenvalues, and in other words, finding the eigenvectors. So for the first set, the eigenvalues that have a multiplicity of 1, we choose a unit vector. So in other words, we just choose a random eigenvector for that eigenvalue and then normalize it. You recall, or you remember how to normalize it. If not, we'll just do it in examples, and hopefully that helps you refresh your memory. Now the eigenvalues with the multiplicity of 2 or greater, so that means k is greater than or equal to 2, we have to find a set of k linearly independent eigenvectors. And if the set is not orthonormal, then we apply the Gram-Schmidt process orthogonalization to get ourselves an orthonormal set. And if you remember, this was I believe it was it last chapter? I think it was it was last chapter with the inner product spaces on how to do that. Again, we are gonna do them in the example videos if you can recall, or you can just look back at the older videos. And so now the previous two steps will produce our orthonormal set of eigenvectors n, which can be used to create our invertible matrix S. That way we can find our diagonal matrix that we all know and love with the special equation, the S inverse AS is equal to D. But because we know that S is orthogonal, then we can substitute the inverse of S to its transpose, and that will give us our diagonal vector. And this becomes so much easier with finding the inverse of S, because if you remember, during the diagonalization examples, especially with the 3x3 matrices, it took us a while just to find the inverse of S, because we had to put it in a super augmented matrix and then find with the identity on one side and then the matrix on the other side, and then we pretty much have to create the inverse matrices, or not the inverse, the identity matrix on the left side, and then whatever is on the right side, we have our inverse. There's so much room for mathematical errors, arithmetic specifically. And so with this one, all you really have to do is just flip two values, and there you go. And so that's pretty much it for this lecture. We are going to do a couple of examples. There are going to be a couple of proofs. I can only think of one right now, but hopefully these proofs will help you solidify what I mean when I discuss about the things here in the lecture. So if you want, you can take a look at those, or you can just go straight to the examples and then take everything as is. But other than that, I will see you guys in the Blackboard.